Welcome back to the lab. We've chosen some comparator thresholds, we've selected a voltage reference. Now let's answer a critical question. How accurate will the temperature monitoring in our 3D printer thermal runaway monitor be? How good is Seth? Well, we're going to be doing some tolerance analysis today to answer exactly that question. Why? Because I like math. No, we're not doing this because I like math. We're doing this tolerance analysis because it's important. The non-idealities and temperature effects and comparators, the thermocouple monitor, the voltage reference, and how the different elements of this circuit combine together, well, that determines the worst case error in temperature as measured by the thermal runaway prevention monitor. So why is that important? Well, because our thermal runaway monitor can't enforce temperatures more accurately than it understands them. So if we set our temperature threshold to 50 degrees Celsius, it's important to know the minimum and maximum temperature that Seth will recognize as 50 degrees Celsius. Now, one device will always trip at the same threshold, but device-to-device variability, if we build 100,000 of these, some of them will tend to trip at slightly higher temperatures and some will tend to trip at slightly lower temperatures. And, well, we need to understand that range. If, for example, you got a version of Seth and he happens to trip at a slightly lower temperature and you set it for 70 degrees C but it trips at 40, well, now you're going to have failed prints. If the opposite's true, if it's tripping at 150 C, well, that might be dangerous. Basically, we need to make sure that the maximum trip temperature will still be safe and the minimum trip temperature won't cause nuisance trips. Knowing the worst case minimum and maximum temperature trip thresholds for the temperature monitor, or the worse than worst case accuracy, now that will allow us to prevent nuisance trips while also maintaining safety. Make sense? We're going to apply a common method of worst case analysis, or WCA, known as EVA or extreme value analysis. Basically, we'll push every component value to its minimum or maximum tolerance, which will cause it to be its minimum or maximum extreme value, and then we'll perform circuit analysis using the most extreme component values possible for each component. Now, the difference between extreme values and the nominal values becomes the tolerance. I mean, that's the bound. That's where it's going to fall. Now, it's very unlikely that every component will be pushed to the worst, most extreme value all at the same time. So sometimes I'm going to roll up the individual error contributors using an RSS method or a root sum square. This error combination method is the geometric mean of all errors, and it depends on an assumption that the errors in a system are random errors. It's important to remember that because not all error contributors are random, like temperature effects. Temperature effects tend to skew all resistors in one direction all at the same time. To perform the bulk of this analysis, we're going to leverage a tool called Smath, which is a symbolic math tool. While we're in my worksheet, let's make a couple pit stops at some critical calculations before we go too far. First, power consumption. I went through the schematic and totaled the current required for the different 5 volt and 12 volt loads. In this case, that's 7.6 milliamps for the 5 volt loads, and I added 20% margin here. Then I made sure that the linear regulator can supply plenty of current for the system. Now that's important because the linear regulator needs to dissipate a lot of energy. Well, a relative lot of energy, more than everything else combined, all in a single component. Yeah, that could be a problem. In this case, I expect that we'll see a 7-degree temperature rise in the linear regulator at the junction. That's plenty of thermal margin. With this determined, I turned my attention to the 12 volt input and summed the total power required for the system. Derating considered, the system will never use more than 180 milliamps, so I selected a 0.7 amp fuse for the power input, resettable type. This provides margin for an auxiliary 12 volt output if a buzzer, a supplementary fan for the 3D printer, or something else is desired for the system. It's basically a general purpose power output for future use. In this case, capable of providing up to half an amp of current at 12 volts before the PTC will have something to say about it. All told, the power supplies involved here are super happy, no issues. Let's keep moving on. We got plenty of margin in the power budget, which means that there's no further analysis or consideration required. What's next? Oh yes! Yes! The meaty temperature tolerance analysis. Good for the soul. So I started by gathering some critical tolerances from the datasheets of critical components, 1% resistors, 4% error from the voltage regulator, comparator input offset voltage, and some tolerance from the 8495 thermocouple monitor. Our analysis begins by combining the random error due to the 1% tolerance on the resistors using the RSS method. These should be relatively random errors, though maybe lot by lot they tend to skew together, so 2 resistors, whatever. We're going to assume them random. This is fine. I translated the input offset error into degrees and combined the fixed errors, which ends up totaling 4 degrees Celsius. Now, this means that at any temperature, the output that we measure, like the voltage output of this thermocouple monitor, might differ from the real temperature by 4 degrees Celsius. And for low temperatures, like 25C, that 4 degree fixed error will be the biggest contributor. Moving on to the ratiometric tolerances, or the tolerances that scale based on how large the output value is. Now I have an RSS combination of the many tolerances from this system, the 4% error from the reference, voltage division error, error due to the hysteresis resistor present in the circuit, error from the 8495 itself. Considering these as independent random errors, I combined them using the RSS method, which established a system-level ratiometric error of about 5.7%. Now, depending on what temperature is being evaluated, these two roll up very differently, so I plotted a couple points in Smath to try to help us visualize what's going on. For the 76 degrees Celsius threshold, which is what I would likely use to monitor a 50 degree heated bed, the minimum threshold that this will trip at was calculated to be 67.6 degrees Celsius, and the maximum came out to 84 degrees. Not bad. For reference, a mechanical thermal cutout, which relies on a material melting, is rated for an absolute tolerance of 5 degrees Celsius. I mean, we're in the ballpark, though to be fair, that is a non-resettable TCO and a fixed threshold, so they can make some design decisions because they don't need the flexibility. Seth has a tolerance of 17 degrees, so 3 times more variance in the trip temperature, but this is a resettable and selectable threshold system. Seems like a pretty decent trade-off. By the way, 17 degrees variance on a 76 degree threshold comes out to a tolerance of plus or minus 11%. Yeah, that fixed error feels pretty punishing here. So I've plotted the error of the temperature threshold as a function of temperature. At a threshold of 16 degrees Celsius, this would exhibit 32% error. Yikes. However, the curve drops down to about 8% error at temperatures above 150C, which feels a lot better. Basically, we're seeing an exponential decay of error that approaches 5.7%. How about at the high end of Seth's temperature range, the highest threshold? Well, at 394C, the maximum trip temperature was calculated to be 420.5 degrees Celsius, and the minimum threshold is 367.5 degrees Celsius, so about a 53 degree spread, or a tolerance of about 6.7%. As far as I'm concerned, this is perfectly acceptable for our application, because remember our problem statement? I think it's reasonable to assume that a fault temperature of 30 degrees above the nominal operating range shouldn't be the difference between normal operation and catastrophic failure. If that's the case, I think that you should be taking a long look at your life decisions and maybe build your system so 30 degrees isn't the difference between burning your house down and everyday life. All this to mean, as long as the threshold being set is 10 to 30 degrees above the operating temperature of the printer, there should be no thermally related nuisance trips. That sounds acceptable to me, especially considering that the heated bed threshold can vary between 76 degrees and 200 degrees nominally. The extruder temperature range varies from 207 degrees C to 393.7, so I think we've safely covered a reasonable range of operating temperatures. And if that doesn't feel right to you, if you need different temperatures, it's a single resistor swap to modify the ranges if required. It's a pretty easy system to mod, pure analog goodness. None of that digital software rubbish. Speaking of rubbish, the main opportunity I see for unplanned error in the system is a result of electromagnetic interference or leakage currents. To help mitigate this, if there's some sort of electrical noise causing glitches on the nodes of this circuit, I made sure to add current limiting resistors and a few microfarads of capacitance, which will provide a relatively long time constant. This combination should help to absorb and ride through transient glitches caused by electromagnetic interference without ruining a print and consequently your day. It's also important that we use an isolated DC power supply to power this, which will minimize the leakage current from the body of the printer leaking back through the temperature monitor. I mean, not that I don't trust that my printer is appropriately isolated, but we better make sure this is. Let's close this out by making a brief stop in drive analysis. Drive analysis is a very important, and it's essentially a method of ensuring that there's sufficient base drive at all the current controlled transistors and enough gate voltage at voltage controlled transistors. Seems like a good idea, right? For the 3904 transistors in this design, the minimum gain at the current level we're working at, which is around 0.1 milliamps, is 40 amps out per 1 amp in of base drive. That is quite a lot of gain. This circuit requires 0.3 milliamps of collector current to fully turn on the PFET. Our circuit provides a base drive current of 0.14 milliamps, so that results in over 1,000% gain margin. I think we'll be fine. That BJT will be saturated, fully driven, no problem. Sweet, that's the current controlled NPN transistor. What about the PMOS FET that's driving the relay coil? Well, since the BJT is fully driven, this means that the PFET should, in theory, be fully driven as well. The DMP 3099 requires 10 volts applied from gate to source to enhance with an RDS, or drain to source resistance, of 65 milliohms. That's plenty. That's sufficiently low that is way more than we need to turn on this relay. So the collector to emitter voltage across the 3904 BJT will be no more than 0.3 volts when saturated, so this means that there's nominally 11.7 volts applied to the PFET. Since we already ensured the BJT is saturated, this is exactly what we should see if we put our DMM in the circuit. With 11.7 volts applied to the gate, this establishes 17% margin above what is required for the PFET to reach 65 milliohms, and I have no further concerns here. That P-channel MOSFET will be on, no worries. The transistors we're using as switches are confirmed to be switching. There's plenty of power available and thermal margin in these power supplies. The temperature tolerance stacks up to be something that isn't extremely wonderful, but is perfectly sufficient for our thermal runaway monitor, which leads me to conclude, wow. Yeah. Looks like we might just have ourselves a solution. I think we can keep pressing on with confidence that the temperature tolerance we've established will meet our needs and solve this problem. Are you getting excited about this project? Because I know I am. I can't wait to finish the detailed design for Seth, and I cannot wait to bring this design into the world. That's all I have for today, but if you like this video and can't wait for more, let me know by getting subscribed, hitting that like button, and leaving a comment down below. Coming up soon, we'll walk through the theory of operation for this temperature monitor and evaluate fault tolerance of this design. I can't wait. If you want to support the channel, consider checking out the products that we featured today through our Amazon affiliate links in the description. It really helps us out a lot. Thank you. Most of all, I hope that you learned something great today, and I hope to see you again soon. Thanks for watching EE for Everyone, and thank you for staying to the end. Bye.